Good afternoon. Welcome, welcome. I'm really excited to be here to talk to you all about Snorkel and our point of view about how we build AI-powered products with foundation models. A little bit about myself. My name is Vincent. I was a founding engineer at Snorkel, started with the company when we were a wee bit research project over at the Stanford AI Lab, and have since then grown to a company that we're privileged to serve some of the largest enterprises in the world to help them with their data development workflows and ML development life cycles. I'll talk a little bit more about that, but just wanted to share that high-level framing, and we'll jump in. So I'll share a little bit of a roadmap for what I'd like to talk about today, and I want to start by setting the stage. You've heard a lot about the current state in the last few days at this conference. Databricks is at the front and center of a lot of the excitement of data and AI today. And I want to talk a little bit about one other perspective on the challenges and opportunities very in line with what you've been hearing in the last few days around current state AI product development. And then I'll dive a little bit deeper to share some of the playbooks that we've seen work in practice. Right? What do data-centric operations and what does data-centric development actually look like for predictive AI problems, for generative AI problems? And hopefully you come away from this talk with a little bit of a clearer understanding of what I mean when I say data as a development interface. So let me jump in. We've seen incredible progress in AI over the last several years. It's driven by increasingly sophisticated and larger language models. These GPT-4s, BERTs, PaLMs of the world are resulting in really, really exciting new experiences, products, and advancements in the AI space in general. We at Snorkel are really excited about these changes. We think it's going to lead to a lot more accessibility, a ton more interest in AI, and overall, it's just been a pedal to the metal accelerant on the gas pedal for AI, for the field and industry in general. In comparison, though, enterprise value from AI is still at a crawl. Right? This is survey data from Gartner over the last 12 months. And the reality for most AI teams is that AI development is still quite slow. Only a portion of projects ever make it to production. And in general, AI investments are expensive and ROI is low. Right? The net result is that AI teams' resources and capacity are significantly limited, and they're not seeing the results that are promised in those really nice and cool demos on Twitter that I'm sure your feeds are also inundated with these days. And so digging a level deeper, for complex, high-accuracy applications, what we're seeing is that foundation models right out of the box, these large language models which make for really, really exciting demos and Twitter-level tweets, don't quite pass the bar for production-grade AI systems and products. These are a few examples that we've worked with anonymized customers on, where out-of-the-box models such as GPT-4, BERT, CLIP don't perform super well for extraction or classification tasks for a variety of data types and domains. And the difference here is that when you actually leverage domain-specific, task-specific high-quality training data, these models can be fine-tuned or adapted to actually unlock production-level accuracy. Right? On a number of these problems, we're seeing an average of 25% or so increase in accuracy scores when you actually adapt or fine-tune or make these models work, again, for an organization-specific data and knowledge. So AI models in general, the way I'd characterize this is if there's some amount of domain complexity, right? If there's some sort of differentiator within an organization, within a product, if there's some private or proprietary data that is really important to unlock in order to drive some sort of differentiation, which for a lot of organizations and teams, that matters, some sort of development or adaptation is required. If there's a high bar for production, right, if the cost of incorrect or hallucinated outputs are really critical in these sensitive or high-stakes environments where AI systems are deployed, again, these models need to be adapted or fine-tuned or developed in some way. AI, just like any employees at any organization, no matter the talent level, needs some amount of training, and models in a lot of the settings that we're seeing also need to be adapted using domain-specific, organization-specific data to get the use cases to production levels and get them across the line. And so if you go one level deeper, what do organizations do today when they actually need to develop their data sets to build AI, right? A lot of what we're seeing is that training data development is still quite manual, still quite slow and expensive. You can imagine that whether you're outsourcing this or doing it in-house, when you're working on these complex, high-accuracy applications, especially when the domain is private or fast-changing or requires some amount of subject matter expertise, manual labeling is still a huge bottleneck to actually get these models over the line and over to production. And so I'm going to talk about a few different approaches that I hope you take away with today about what I call data-centric development, which is really the idea of focusing on training data as a critical pillar to make AI work for your data, your knowledge. And two, I'm going to talk about programmatic interfaces for development. So rather than manually labeling, cleaning, sampling data, one by one, with really expensive subject matter experts, think doctors, lawyers, financial experts, what I'd like to put forward is the idea that a programmatic interface to labeling and scaling domain expertise is a far more viable way to develop and curate your training data sets. The high-level way I like to think about this is actually a fundamental shift to how I think about building AI-powered products. It's all about programming your AI with your data. And it starts, again, with this data-centric development, right? This notion that your training data is at the center of everything you're working on. And two, it's around this idea of programmatic new interfaces for scaling up and automating these sources of signal at the end of the day. So what does this actually look like for product teams and organizations? We're finding that most organizations are actually getting access to models and infrastructure in large part due to our friends here at Databricks. What truly differentiates a lot of organizations is actually their specific training data. But most enterprise AI stacks actually don't have a scalable way to develop data based on, again, their knowledge, tasks, and constraints. And so in practice, we're going to talk about some of these data-centric operations today, which I view as the highest leverage interfaces for AI teams to actually drive results, get some of these models to production, and leverage a lot of the excitement that we're seeing and true magic, right, that's in these foundation and large language models, and get them to a state where they're viable for real applications. So in the next section, I'll share a little bit about some concrete playbooks that we found at Snorkel actually work for our customers, right, that actually are helpful to taking what starts out as a demo and a really cool idea to something that's actually production grade and critically maintainable over time. To do that, I'm first going to frame different types of use cases. Right? I'd like to actually explain the difference in our view between what we call generative versus predictive AI. You probably see a lot about generative AI on Twitter these days. I want to differentiate that from what I'll call predictive AI, which has a goal of producing some sort of closed schema output. Right? Think of a label schema that has a fixed schema for some extraction or classification problem. This is quite common in, say, document extraction problems. I want to pull out these values from 10Ks, from invoices. I want to triage or automate the processing of these documents. These are often problems where you have some sort of closed fixed schema that you want to make some sort of prediction against. On the other hand, generative AI use cases are those which I characterize as completing some sort of open schema based on a contextual prompt. So the output is much more open-ended here, right? It could be text, image, audio. We're seeing a lot of really exciting different applications of generative AI these days, and we're still in the early days. But the key idea here is, you're prompting with some sort of input. Maybe it's a quick Q&A prompt. Maybe it's an ask for summarization or rephrasing. Maybe it's a code, comment that you actually want to use to generate additional code in a coding assistant. These are two actually fundamentally different use cases that we tend to work with our customers and users to differentiate when thinking about how to apply foundation models, large language models most effectively. And so let me talk about one example, one case study on the predictive side just to start. We worked with one user of ours, a data and technology company who wanted to work with us to actually build some predictive AI applications to classify video metadata. Think, a bunch of YouTube-style videos into 600 plus overlapping classes based on some ontology, right? So you can imagine these are a lot of classes. There's a lot of overlap between them. There's a hierarchy implicit. It was quite a messy and complex schema, closed schema to actually use as an output target. And using Snorkel, cutting to the outcome here, we were actually able to use a lot of the methods that I'm showing you to get to some outcome with production-grade accuracy with only a few weeks of development, which by our customer standards were far and above what they were used to in terms of these types of problems. So first, let me talk about some of the challenges that this customer hit in the previous state. To start, one of the hardest parts of this problem was actually tied to the schema, right, which is often really critical for these types of predictive AI problems. In this case, we had a schema, an ontology or taxonomy of video categories, which overlapped a bit. Some of it was intentional, right? The classes actually did intentionally overlap, right? There might be, some classes related to travel types, and different types might actually have some amount of overlap. And there was also some non-intentional overlap, right? These are classes that may have drifted over time or have become a little bit unwieldy, or because of some human error, right, are a little bit of a source of kind of schema debt, if you will, in this type of system. And overall, we were dealing with 600 classes, which is quite a lot for a production-grade system and hard to manage, but is not that uncommon, right, for these enterprise-grade, production-ready applications. So the complexity and changing requirements of the schema were one of the key challenges that we were faced with up front. A second challenge is what I'd like to characterize as the cold start problem, right? This problem with manual labeling, especially in this 600 class overlapping multi-label problem, it was really challenging to actually scale up and generate ground truth manual labels for the setting and manage the errors that came out of that process, right? This is a process that, again, whether it was outsourced or in-house, required a ton of manual effort, time, and cost to actually get something that was viable to even start training ML models. And finally, when you actually got to that first model, the iteration process looked a little bit like whack-a-mole, whether you were dealing with hyperparameter tuning with traditional ML models, right, the classic grid or random searches, or you were doing more advanced prompt engineering with your favorite library out there. It wasn't really satisfying to use either of these approaches to actually drive towards some sort of robust ML model where we had some guarantees around accuracy, performance over critical slices. This didn't really meet the bar in terms of enterprise grade or a product that we could be comfortable with shipping to production. And so zooming ahead, right, what we ended up working with this customer was a process that we call data-centric development. And I'll walk through each one of these steps with their use case in mind in the next few steps. The first step was all about actually defining the task, connecting to their data sources, and choosing an initial foundation model to warm start the problem. And what I mean by this is you can actually leverage foundation models as a source in predictive problems of an initial set of weak labels. Right? In this case, we actually leveraged foundation models, prompted them, used some zero-shot prompts in many cases to jumpstart the training data creation process. In some cases, we did a little bit of prompt engineering. It was noisy, it was messy, but that was OK. Right? We used that as a starting point to help us overcome a little bit of this cold start problem. This wasn't production quality by any means, but it certainly helped us get to that 40, 50, 60% range, which at least gave us a starting point that wasn't zero. Critically, the next step here was to actually leverage a set of guided analysis tools to understand where the model errors actually lived. So once you actually get that initial model, the reason I said it was OK that it wasn't perfect was because we had an intentional step to correct it. This next step was all about discovering where to look next, where to label next, what hotspots in your data set are actually causing issues. And you'll start to notice that the whole iteration loop here is anchored on your specific data, right? The highest leverage way to actually make improvements, figure out what changes you could be making to drive high performance improvements is by doing the hard work and looking at the data and understanding those hotspots. And so at Snorkel, right, we've built up a number of these what we call guided error analysis tools, which eliminate the need for these cumbersome notebooks and spreadsheets to actually understand where errors are happening, right? Intuitively, these are a number of ML techniques that have been remixed, right? Active learning-based techniques, right? We might use model confidence or embeddings to find error hotspots where the model's overvoting or making mistakes or misaligned with certain amounts of training data. We might allow users to specify critical and meaningful error slices, right, based on semantically meaningful slices of their data and then help them improve from there. These are all techniques that we wanted to use to help, again, our users understand where to look next in terms of where that initial warm-started model was making mistakes. And once you've actually identified those error hotspots, the next step is actually correct them, right? And so, this is where we lean on technologies that we've built up on the lab side around weak supervision, right? This idea that you can actually use these more programmatic, more scalable forms of supervision to correct errors in your data set. And I'll talk a little bit more about what this means in the next slide. So what I mean by weak supervision or programmatic labeling here is you actually have the ability to apply all different sources of knowledge to correct errors in your data set, right? You can imagine, let's go back to our video classification problem. I, as a domain expert or product person within the customer environment, could say, hey, if free cash shows up in the description of my video, it's probably an advertisement, probably spam. Let me express that heuristic, right, as a function, as something that I actually capture as knowledge in my system. I can use a prompt, right? I can actually use existing models, use those representations as yet again another noisy source of supervision to say, hey, what sport does this actual description remind you of, and map that to a noisy or weak label. I could use ontologies or existing resources, right? A lot of these organizations that we've worked with actually have access to knowledge bases, existing resources, legacy systems, these rule-based or regex-based systems. All of that can be used in a little bit of a noisy way to, again, route data to a noisy or weak label. And finally, you could imagine using embeddings to kind of explore the data space and, again, treat this as a way to capture noisy or weak supervision. At the end of the day, all of these sources of supervision can be captured in what we call a programmatic labeling function, right? So instead of manually labeling one by one, you express these rules, you express these heuristics, and those ends up being the inputs to your system. Now, critically, all of these rules are inherently noisy, and that's where a lot of the academic work that is ongoing in many ways around weak supervision come into play to actually help you denoise and aggregate and combine these rules to produce high-quality training data without the need to, say, manually audit every single example. So zooming out for a second, right, let's assume that we've gone through this iteration loop. We've done this step of discovering errors, correcting them, discovering errors, correcting them. This is an iterative feedback loop, right? This is a new paradigm for a lot of our customers, especially this one, where before they were tweaking the hyperparameters, looking at the tensor boards. I've been there. It's fun in some cases, but maybe unsatisfying in others. And once you're ready with a model that feels like it's hit the quality bar that you're comfortable with, we actually had a few options in this case for deployment, right? We could export the training data to train another model. We could deploy a smaller ML model and distill down the knowledge in that foundation model for a more cost-effective setting, or we could fine-tune the original open source or proprietary foundation model, depending on the needs of our use case. So for this problem, we actually considered the trade-off, right? We want to use the foundation model. Do we want to fine-tune or distill this in practice? And the trade-off axes we considered were all about, one, privacy. Do we feel OK about sending this data to a third-party provider and having it fine-tuned and potentially leaking what is secret or unique to our organization? Two was cost, right? More parameters often means more cost. And was this technology company, it was a startup still, but was this technology company comfortable with paying the inference and training costs for ongoing maintenance of this model? And three, what are your quality requirements, right? Do you care about generalizable performance across a number of tasks in a broader sense, or do you care more about task-specific, narrow quality? And in this specific setting, right, the two axes that mattered most to us were cost, right? We wanted to deploy something that was actually reasonable to maintain over time and that we could manage costs around. And two, quality. We actually cared a lot more about task-specific accuracy, specifically for this video classification problem, rather than, say, generalized Q&A for a general-purpose foundation model or chatbot. So in this case, it actually made a lot of sense to take the training data that we had generated in Snorkel, treat that as a form of distilled knowledge, and use that to distill down the knowledge in a foundation model to deploy something that was a little bit more cost-effective and inference-friendly, and put that in production instead. And so once we had this model in production, there was actually an additional step here, right? And this is what I call continuous adaptation. This is the step of maintaining valuable and effective models and updating them regularly, right? With a system like this, where you have a data development loop, when you're leveraging these programmatic sources of supervision, this is actually far easier than relabeling your entire data set, right? The key idea that I like to think back to here is it kind of looks and feels like debugging and refactoring code. You know, you're able to measure where there are mistakes, right? Where there are maybe overlaps between classes. You might be able to measure inter-annotator agreement over time, right? To understand, hey, where are my classes actually well separable, and when do I need to kind of rethink this? You might have new business requirements come in, right? That just mandate a new change in the schema. When you're labeling your data with these rules or heuristics, these labeling functions, changing the schema is actually relatively straightforward. It kind of looks like, you know, changing the output type in a dropdown, or remixing a few of the labels. And because they're all functions, it's far, far easier than, say, relabeling all of your data at once. And so this mental model that I had around debugging and refactoring your code and programming your data, programming your AI with data, comes into a really, really, really helpful scenario in this case, where, again, we needed to update the schema over time continuously. So ultimately, the playbook for building this specific predictive AI problem looked like this end-to-end pipeline for data development, right? We started with their data, their models, and a set of foundation models which were generic but powerful. We were able to actually warmstart development, a sort of foundation model-assisted labeling approach, to get started using those foundation models. That wasn't perfect, and we expected that. But then we were able to use this, what I'll call inner loop for iteration, right? This loop to say, let me find what to do next. Let me look at the error hotspots based on confidence, based on active learning, based on ground truth issues, based on these fancier techniques using embeddings. Let me take those approaches and actually figure out what to do next. And then let me correct those errors using programmatic sources of supervision. Let me actually program my AI by nudging it in certain directions with these heuristics, these functions. Once we were ready to put this model into production, we were able to choose, hey, do I want to fine-tune or distill? And based on the problem's trade-offs, we were able to say, hey, a distilled model makes a lot of sense here. And ultimately, when we needed to change the schema, because we had leaned on these more programmatic sources of supervision, it was far easier to actually adapt over time. So hopefully this mental model is starting to make sense, right? What I mean when I say data-centric iteration and development is all about looking at your data and correcting errors. And the model itself, right, you can imagine is actually much more push button, right? You can kick off the job, kick off the search, but most of your time and energy is actually spent on the data. So what do I mean for data development when I move on to generative AI, right? What changes, what stays the same? You've probably heard in a lot of settings that there are a number of techniques for adapting foundation models, right? From fine-tuning to instruction tuning to general pre-training. These are all techniques that are quite exciting, and from a high-level perspective, one thing, one playbook or strategy that we found to be really helpful when talking to our customers is to focus on the highest ROI for your use case or product goals, right? Each one of these operations contributes different types of knowledge and addresses different types of issues. For example, on the bottom of the stack are more generic operations, such as generic pre-training. This is where intuitively your FM is learning to read and write, right? It's kind of learning from a general purpose corpus, possibly the whole internet, of public data, Reddit data, Wikipedia data. And it's learning these general principles about how to interpret language and do this kind of language model type objective. As you move up the stack, you can imagine wanting to pre-train one of these models if you have a massive corpus of internal documents on the language, on the nuances, on the specific language and domain-specific data of your organization, right? This is what we call domain pre-training. An enterprise, a specific organization wants to train their own model, right? There's a recent paper called Bloomberg GPT, which did exactly this. They pre-trained on their specific data sets and saw some improvements over, again, tasks that were aligned to their organization, which makes a lot of sense intuitively. And as you move up the stack, right, some of these steps around instruction tuning or task-specific tuning are all about fine-tuning and preparing these models to perform much narrower and specific AI tasks that might work well for specific use cases. Now, in practice, what we often recommend to customers is to say, hey, what are you trying to do? What is the practical AI problem you're trying to solve? And move top to bottom and understand what layer of the stack you need to be operating at. And often, this actually helps cut through some of the noise around, hey, do I need to build my own LLM? Do I need to fine tune? What should I actually do to drive development for the application I'm trying to work on? Now, critically, this might not be a surprise coming from me, data is still the determiner of success at every one of these stages, right? Every one of these, what I'll call training operations, can be executed with a pretty standard algorithm, right? The LoRa's and all these algorithms in the world are out there on GitHub. But the thing that's not out there on GitHub is the proprietary, private, domain-specific data sets that different organizations make use of to actually make their AIs useful and differentiated, right? No matter how good your training code or how efficient your environment is, you're not going to get to a differentiated product or a high-quality model unless you have your own data that you're training over. And so one helpful exercise that we've worked with our customers and users on is to separate what we call model-centric versus data-centric operations for a lot of these foundation model development settings, right? Again, both are necessary, but often the data-centric operations are behind the curtain or less obvious to folks, right? These are the labeling, tagging, and slicing functions that are necessary to actually get a fine-tuned model out there, right? For instruction tuning, these are the cleaning and ranking, RLHF-style feedback processes that, again, are critical to actually curating and generating the right instructions in the first place. And for pre-training, you still need some degree of slicing, sampling, filtering to actually get to results that matter for a specific organization. Too often, these data-centric operations are treated as and performed as a little bit of an afterthought, a little bit of, janitorial data munging or pre-work. And our claim here is that this is actually the central part of any organization's high-leverage effort, right? This is where most of the time and energy should be spent, whether you're building predictive AI apps or generative apps. This is where the leverage is, right, in a specific organization's product. And so going one level deeper, right, just like we talked about before, there are benefits to transforming these operations from manual and ad hoc to a little bit more programmatic and systematic. You can imagine what we call as sampling or slicing, right? Choosing the right distribution that you want to train on over large samples of data. If you capture these as slicing functions, they're not just more scalable, they're also more auditable and adaptable over time. Filtering, right, a very similar sort of response. Do you want to accept or reject certain responses to help with instruction tuning an agent, for example? Capturing these pieces of domain knowledge as artifacts that can be scalable is a really high leverage way to actually build these types of systems. Same with ranking, same with labeling in general. The key idea here is that each one of these steps, each one of these data-centric operations, when you make them first-class, programmatic, and systematic, it's not just a kind of scale benefit, but for teams who are working on this and maintaining these systems over time, we found this to be a really, really high leverage way to actually build these types of systems in practice. And so I'll point to one paper over here from our friends over at Berkeley. They showed that instruction tuning on the right data actually is an extremely high leverage way to train a foundation model, right? They showed that you can achieve 4x faster speed, 4x cheaper costs, and better quality just from choosing the right subset of data to train on, right? So bigger isn't always better in these cases, and a lot of the time, the most practical thing for organizations to do is to, again, make their data work for them, whether it's labeling, cleaning, sampling, tuning. All of that is something that is a really high leverage exercise for a specific organization. So zooming out, at the end of the day, I really want to anchor on this idea that the highest leverage way that we found, customers of ours, users of ours, to build AI-powered products is what we call data-centric development, right? This is the process of iteratively labeling and developing your data sets, right, using that inner loop that I talked about earlier, right, the discover errors and correct them with programmatic sources of supervision. And it's actually leveraging and taking advantage of these programmatic interfaces, right, rather than the manual and ad hoc sources of manual correction that you often see in a lot of organizations. Capturing and scaling domain expertise with these functional or heuristic-based approaches is actually quite effective to scaling out these sorts of processes. And at the end of the day, the outcome here for teams is that they end up programming their AI with their data. And that's a scalable way to actually build AI-powered products that are differentiated for a specific team or organization. by all accounts, right, we're still very, very early in the industry, in research, right, in the journey of what AI development looks like. But this is the stack that we're starting to see emerge for a lot of our customers and for a lot of teams that we've been working with, right? A lot of what you saw here today, right, was built up from experiences, hands-on experiences, working with our own customers, working on our data development platform, where we focus on this, data development layer. And I'm really excited to see where the industry goes, right, from FM providers to data lakehouse and warehouse, compute providers, to the cloud providers of the world. There's a lot of really exciting momentum, and just practically from what we've seen, the data isn't going away, and it's going to continue being a really important part of every organization's journey to making these models actually work. Thanks so much, folks. I really enjoyed my time. Please do reach out. I've signed for some questions, so thanks so much.